So welcome everyone to this practical guidelines for heat pump installations sponsored by Victorian Government, DELWP, that's the department for there from Victorian Government, and the Victorian Energy Upgrades. My name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity. We're a non-for-profit organisation that works with improving energy productivity. I'd like to start this webinar with a acknowledgement of country, and together as the team presenting to you today, we'd like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community. And we will pay our respects to their elders, past, present and emerging. And I'm sure you'll all join me there. And if you'd like to acknowledge the traditional custodians of the lands where you are today, feel free to do so in the chat. For me, that's the Darramurrugal people in the northern suburbs of Sydney. Mentioned before, A2EP is a non-for-profit organisation funded by these members, and we have a lovely wide range of members that share our vision to improve energy productivity within Australia. And so this is helping bring this webinar to you today, but the main reason why we're here for is thanks to the support from the Victorian Government. Jack Brown, you're online there. We'd just like to say a quick intro for the scheme and the work that we've been doing here and what DELWP is working on.
Thanks, Jared, and good afternoon to everyone who's online. I'm Jack Brown, Manager Energy Efficiency Technologies at the Victorian Department of Environment, Land, Water and Planning, or DELWP. And I lead the team who work on new and revised activities for the Victorian Energy Upgrades, or VEU program. It is my pleasure to join you today and to work with Jared and the A2EP team on this really important project, and also on the second webinar that we've hosted. Since the first webinar was held on 21st of June, Victoria has released its gas substitution roadmap, and that notes the importance of the VEU program in increasing electrification for Victoria. So the VEU commercial industrial heat pump water heater activity, which we'll talk about today, provides a really fantastic opportunity for commercial industrial sites to improve their gas efficiency and reduce their energy costs. And as I noted in the first webinar, the VEU program wants to see this done in the right way. So we want to see the application of heat pump water heater technologies done appropriately, including in design, selection and installation phases. It's really pleasing to see the great lineup of speakers we have today in the webinar. My thanks to them for providing their time to us. I do look forward to hearing their perspectives and experiences on the use of heat pump water heaters. I think that will be useful to the audience as well. Thanks to all of you in taking the time to participate in the webinar. I hope you find it useful. Jared and I know, do look forward to releasing the guidance document that will support the work we've done and what we've discussed in the webinars. So thanks, Jared, and back to you.
Brilliant. Thanks for joining us today, Jack, and you'll be online all the time. If we have some questions towards the end, we'll bring you in as needed. And of course, today is going to be recorded and the slides will go out, so that'll be a nice resource for you all, along with the guidelines, which we're hoping to have published in the next few weeks. So joining me today, we've got Dr. Ahmed Mujiri, who Ahmed and myself and with our project leader has been working hard over the last 3 months or so, doing a lot of industry outreach and understanding where suppliers are at and energy users are at when it comes to heat pumps, and trying to find the best practice and distill that down to a guide. I'll have introduce Ahmed in a moment and take us through that first webinar that we've done, and a little bit more about the guides and what have you. But just to sort of summarize where we're at and what we're trying to help you all achieve here is help you on this journey, this buyer's journey. It is new technology for a lot, because the heat pumps, whilst they've been around for many years, they're now being applied more for different applications. Most people will have a reverse cycle air conditioner in their home, so yes, most people already have a heat pump, but to apply the heat pump to different industry and commercial applications does require a different skill set and a different way of thinking. So that's what we're trying to do, is really help people on this journey, and people will be at different stages. Maybe just not sure about awareness and what heat pumps can do. Maybe they've decided, yes, I want to have a heat pump, but how do I integrate that? How do I make it economical? And how do I do the best installation possible? Great, now you've got that. Now it's a case of, well, how do I make sure that's procured correctly, and I get value for money, and I get my vendor owning the performance guarantees and warranties and making sure I'm really well supported. And then going through the installation, make sure the right contractor is in place, and they know how to do that installation, and understanding the differences between installing what they may have done in the past, the boiler, versus this heat pump. And then finally, there's this community needed to develop the knowledge of the operations and maintenance, or O&M, on operating these heat pumps and how best to maintain them. So it's quite a journey, and I think I'd suggest most people are in that first couple of phases still when it comes to different commercial and industrial applications, and we're certainly trying to help that along. Ahmed, this is that's part of the journey now, but Ahmed, could I get you to come and just take us through some of the deliverables that we'll be able to do to help people through that journey?
Sure. Thank you.
Okay.
Sure. Is my screen shared now? Do you see my screen?
It is.
Okay, excellent. Thank you very much, Jared, for introducing the project and the deliverables. And also thank you, Jack, for explaining how we have been working with you guys over there in DELWP to develop this project in a way that I believe will be practical and useful sort of document and the body of knowledge for relatively general audience who are or may be interested in upgrading their thermal systems to use heat pump technologies. As you guys explained, one of the main deliverables that we are going to release soon is a technical guidelines. And that technical guideline have been developed by the A2EP in a close collaboration with the industry. Some of those industry people are now on this panel. Some of them will actually talk later during this webinar. And we have consulted extensively with them with this purpose in mind, that we want to make these guidelines practical based on real experience. And we learn from them, we learn what problems have been observed there, and be able to deliver something that is actually useful for the people, for the general audience. We have divided that guideline into different sections. We have talked about general design considerations for heat pumps, and we have talked about specific design considerations for specific sectors. We have covered 3 major sectors in this work: agriculture, focusing on dairy farms, aquatic centers, and multi-unit residential buildings. For all of these design considerations and heat pump upgrade projects, we have also included a procurement guide helping to understand how to design, select, purchase, and get the heat pump, and look at different aspects of a successful heat pump implementation. We will look at those procurement guidelines in a few slides during this webinar. As you explained, Jared, we have included 2 webinars in this project. The first one we delivered a month ago, as Jack mentioned. This is the second webinar. The first webinar, we talked about those basic heat pump operation and explain how heat pumps operate, what their unique features are, how can they be used for savings of energy and reducing emissions, and also saving running costs. We talked the design considerations, but in a general terms, not for any specific application. We also introduced the procedures to benefit from the VEU program, and how some heat pump adopters can actually benefit the Victorian Energy Efficiency certificates to improve the economics of their heat pump installations. So just very briefly again, to go in a few seconds through the important aspects of the guideline that will be released soon. The main purpose is to raise awareness among the public. As you mentioned, Jared, we include that in the guideline, in the document. We explain features of heat pumps, their potential. We talk about their integration, and we deliver the knowledge about their integration for different sectors that have been covered in this work for those 3 sectors. We also introduce the procurement knowledge, as I mentioned, through explanations and decision matrices, and also some of the installation knowledge that you, Jared, mentioned. They will be, we are confident that we have covered enough material on these aspects, and I personally am very hopeful that it will be very beneficial for the general public to deliver these aspects of the knowledge in this area. I think, Jared, that is enough for me, and like from my side at the moment. I hand it over back to you.
Very good, thank you, Ahmed. That should have come back for my slide now. So today we are presenting the 3 cases, a multi-unit or actually more of a commercial building and domestic hot water for that, an aquatic centre case study and a dairy farm. Each of these, whilst very separate applications, have a lot of crossover learnings that you can apply to your everyday heat pump situation. So look forward to exploring those shortly. One thing we wanted to just introduce to you now was a procurement guide. As part of the guidelines that will be produced, we will run through a sample procurement guide, which helps take you through the different elements to review within a heat pump and the supply. It is a bit more equipment focused rather than the total installation. So if you're looking at this as much buying off a heat pump vendor, not a contractor, but it will help you guide you towards some of the important parts that you need to review. And I draw your attention to things like the terms and conditions, making sure that you've got some clear warranty obligations, making sure that you've got things like retention for final payment until the performance guarantees is met. A few tips and things like that we think would help with your procurement journey there of this new technology. Also with a little bit more detail there, and apologies for the font, but you'll be able to see that when the guide comes out, really going through a few of the more technical aspects and specifications that you are likely to come across with a heat pump. And of course, some vendors may not offer this information, but that's what we put that there for, to prompt so that you do get that information and make sure you really understand what you are purchasing. Okay, so let's get into the first case study, and let's start hearing from some presenters who are actually out there doing this. And the first one we're going to go through is like a commercial building, and this one a multi-residential building. And if we have a quick overview of where that industry is at right now, I mean, it is quite a tough retrofit business, but we certainly see lots of momentum happening for new build heading towards heat pump for space heating and domestic hot water. Right now, the existing stock, particularly in Victoria, it would be dominated by instant gas, and that does make quite a difficult retrofit. But there is still lots and lots of opportunities out there. Certainly, we say that there's, when you look at centralizing the heating system, there is energy efficiencies to be gained and opportunities there as well. As I mentioned, difficult retrofit, but it certainly can be done. So let's kick this off. Today we're going to talk to, we've got three speakers here who have lived through a couple of installations. And the first introduction we've got is Norm Anderson, the Director for Energy Smart Water, who has come off the bench, even though he's sick with our old friend Corona there. But Norm's soldiering on and joining us today. We've also got Chun Go, the General Manager, and one of their sister companies, Thermal Energy Solutions, Peter Toe, has joined there and is going to take us through a project. Peter, could I get you to share your screen and take us through your case where you've installed heat pumps in some buildings?
No worries.
Looking good. Okay, you're there.
You want me to kick off, Jared?
Yeah, go for it, guys. I couldn't hear Peter.
Yeah, look, it's Norm Anderson here, Director of ESW and TESS. Just a little bit about Energy Smart Water. We're a global import and supply company, supplying into not only Australia, a lot of products from Europe and other countries, but also into America, most of Asia, and different things. So we've had a pretty big place in the space of commercial heat pumps, especially in Singapore and Asia, where we've been doing commercial heat pumps for probably about the last 14 years, obviously with our tanks and our systems, all the stuff that we designed here many years ago. ESW and our principal product, which was the Enermax Smart Cube, which is integrated with the heat pump, was originally brought to the country 20 years ago. So we've had a lot of success with that product, and it blends in quite well. Where TESS fits in, that's another company that we own. That is where Peter is our senior engineer. We do designs, we build systems, and we supply, we install, we supply to the market as well. So just a bit of a brief intro on that. I guess one of the things that we see a lot of too, Jared, in the we also have another commercial hot water company as well. We're a major plumbing contractor in Melbourne as well. We look after probably around about 2,000 commercial buildings in residential sectors at the moment, but we're really at the face of dealing with customers every day, and we see our ratio for tendering changeovers and new work at the moment is probably around about 75 to 80% now pushed towards heat pumps, to where it was with gas probably more or less 2 or 3 years ago. So there is a big shift. We've done many projects with heat pumps. I think Pete and Sean are going to run through the introduction with you to talk a little bit more about what we've done, some of the case studies. But we've done many projects. One of the biggest ones we've done is the Youth Detention Centre down at Lara, with about 26 heat pump sets with our tanks. And the job's working through the commissioning phase at the moment with no issues. But look, I'm going to hand over to Sean and Pete and take you through the presentation and explain a little bit more about our system.
All right. Good afternoon, everyone. So thanks for attending the webinar today. So like what Norm had mentioned, we have been supplying all the this system, heat pump and thermal storage, to industrials, commercials, residential building, hospitals, aged care, and also defense and detention center. So this is basically what we've been doing. So recently we had quite a long number of heat pump projects that in the CBD. So we had successfully delivered that and able to have a proven result that saved the energy. So as you can see on the slide here, you can see that's the thermal storage that we have, and we call it as thermal battery, which we found that in a good heat pump system, heat pump have to be one of the equipment that able to produce a very good heat source. And then with the good heat source, you have to keep it, you have to store it in the proper thermal storage. So only you can effectively and efficiently use the heat source that you generated. Else the heat source will, if you don't have a proper storage on heat pump system, you're going to waste the heat that you generated as well. So it have to be a combined system that work it out. So if you look at the slide over here, heat pump system, there are direct system and indirect system. So we are focusing more on the indirect system, where if you look at the animation here, the heat pump itself, what we design is the heat pump will only run, only heat up the water in the tank, which is not a potable water, is a water that holding in the tank to store the heating, the thermal energy. So your potable water basically is running to the coil. You can see the blue arrow coming down, going into the coil, heat exchanger coil, pick up the source of heat, and then come out, you have instantaneously, you have hot water. So this is how our system design. So let's deep into the project that we recently completed, 101 Collins Street. So this is a heat pump system basically to replace gas system that existing gas system in the building. So 101 Collins Street, Melbourne, located in the Melbourne of CBD of the Melbourne. So original system was a 7,000 liter clarifier, gas clarifier. So it's mechanical heating plant, and this one, the system is the first stage of the project. So the first stage is only from we are supplying 24 stories hot water to the basin. So it's from level 31 to level 53 of the building. So this one, we have saved them 81% of their energy usage. So if you look at this, what we do is we use 3 of the 19 kilowatt commercial grade heat pump, high temperature heat pump, which generate up to 80 degrees C. And then we store the energy in our thermal storage tank. So only 4 storage tanks. So this one will able to supply to 23 stories of hot water for your basin. So this is stage 1. So stage 2 will be upcoming, where it's going to supply from level 13 to 34, which would be something similar as well. So for this system, we have been operating, heat pump would be operating very minimal, where we heat up the water up to 75 to 80 degrees, and then the rest will be topping up to 85 maximum degree from the solar PV. So the solar PV will have will generate the power to run on the heating element as well. So it's a combination of system. So with this, we had successfully awarded with the National Energy Efficient Award recently. So the advisor is from AG Cum Advisory as a consultant, and the client is 101 Collins. So from this one, the original system, old system, they're using about 356 gigajoule of gas per annum, just based on this 23 level of the building. The total building will be 3 stage. So total building height is 53 levels. So our system is sitting on the rooftop. So with this system, we save them, the cost saving itself, if we base on the current gas price, we save them about 50–60%. So energy saving is 81%.
Sean, can I just jump in for a sec?
Yep, sure.
One of the other things, can you just go back a slide, Pete? One of the other things that we've considered too, Jared, is we do have 3 size ranges of heat pumps, so 19 kilowatt, 32 and 64 kilowatt. But when we're trying to retrofit a building and future-proof a building, we've chosen that we'd rather use the 19 kilowatt and build up more modular systems, because we've got to be able to get the heat pump into the building and also be able to get the heat pump out of the building. So there's no point having a monstrous heat pump if we can't get it into the location. So most of our designs now are focused around the 19 kilowatt heat pump in a modular sort of phase. So you'll see that in some of the other projects we have as well. Gotcha.
Yep. So what Nom said is because the for this building itself, there's the access to the roof is only through the lift, service lift. So that's why a modular system would be better, and we can prefabricate all the system in our factory in Domana. So what we do is we prefab all the headers, we prefab all the tanks on the skid, we mock it up. So basically, when we deliver to the site, it's on a loose. We just bring it in. The site plumber or trades people, they just, according to our drawing, plug it in. It's basically plug and play. So the thing is not only you saving time and you save material on site, because we know that trades will cost you a lot when they work on site. So eliminate all those trouble for the customer and reduce their project costs on installation. So yeah, so the next one will be Triple Two exhibition. I let Peter to continue on this one, Pete.
Hi, thank you, Shane. So this is another project in the Melbourne CBD is also Triple Two Exhibition Street. As you can see, the previous system is a combination of a gas storage and electric resistive system. And we replaced that with 2 tanks and 2 of the 19 kilowatt heat pumps. So in this case, 1,000 liter storage and 38 kilowatt of a heat pump capacity. And the uniqueness of this project is that we're actually taking heat recovery from a mechanical plant to offset the heat pump runtime at the same time as well. So this schematic drawing shows how the system being laid out. As you can see, we've got a heat pump to heat up the tank, storage tank. At the same time as well, we've got a mechanical line, as you see in orange line, that heat up the tank. So mechanical line usually runs at higher temperature. They're running somewhere around 70 degrees to 75 degrees Celsius. So we try to capture that energy as much as we can to heat up the tank. And if the tank does drop in temperature down to, for example, 60 degrees, then the heat pump will top up the temperature up to 65. As you can see, most of our systems are prefab, and this is to control the environment in a way. We know that this is a new technology. It's a new system that we deliver to the installer to install them. And the one way to control that, if we prefab most of the skid, as you can see in the photos, we prefab all the pipeworks on the skid, and we deliver them to site and place them in there so that the installing plumber will then just need to do the connection from the heat pump to the storage tanks. This is an example of a June, which is a very recent data last month that we took a snapshot of it, and we're trying to determine how much of the gas consumption it will reduce. So you can see the gas consumption from 2012 all the way to 2022. You can see the patterns that go on from that as well. And at the same time, so you can see how the electricity consumption drops. The usage drops as well at the same time. So at the time of this data, the building was at 75% occupancy, and we still managed to reduce pretty much the gas, 55% of gas consumption of the whole building. The mechanical plant is still running on gas, and they're looking to phase out that mechanical plant as well. So in total wise, we're looking at the 49% reduction in the total energy consumption. According to the building manager, the hot water upgrade is the only major upgrade that's happening from when we install the hot water till June. So they haven't had any upgrades in between then. So we still looking to dissect in terms of especially the electricity consumption to see what is the actual increase in electricity consumption. But we also notice as well, besides we've got an offset from mechanical plant that able to reduce that heat pump runtime quite significantly. So this is still the other projects that we have done in terms of 720 Burke Street, just to show how we are able to modulate the system accordingly. So we prefab all this system and we place it on site, and then the installing plumber just connect them up the pipework. So we make it very easy for the installing plumber and reduce troubleshooting on site as well, and also control the installation process, on-site installation process.
So just to add on, Peter, roll it back. The photo on the right-hand side, that is the one in the youth prison. So this is the youth prison project. So this is just one part of the plan that we put up. So there are a total of over 23 heat pumps that we put into this area. Yep, thank you.
Yeah. So in terms of these two projects, the main challenges that we know that is that the difficulty of system monitoring. So what we learned is that initially we thought that the BMS was able to monitor every aspect of the energy within the system or within the building. What we learned the hard way is that the BMS does not do that. And in fact, one of the challenges is actually BMS integration as well, how to integrate the Modbus system from a heat pump to the BMS system in a building. It is one of the areas that we are looking to improve to how to make it easier for the building managers and the BMS to be able to integrate the system properly. And one of the other things as well is the equipment footprint and access is one of the major areas that we look at. Heat pump require a much bigger footprint compared to a gas storage or gas system. So we need to find a proper location where we can get a proper fresh air and proper cool air discharge, a proper pathway, chart out a proper pathway to make sure that the heat pump installation get a proper ventilation as well. And site access where we're able to get the equipment from ground floor all the way to the roof. A lot of these equipments, plumbing equipment is still placed on the roof. So we need to keep that in mind, how to reduce the installation cost and get equipment from ground floor up there. And the next thing is to justify the higher capex for the heat pump. So we do run an ROI and running cost before we install the system as well, so to make sure the clients is informed in terms of like, by spending high expenditure, what will be the expected payback for that system.
Okay.
And and last slide is that the lesson learned is that we learned is that probably we need to implement part of MMV to the project to better understanding in terms of the energy consumption of the system. And and plan monitoring at the start of the project will be useful as well, so that we for building manager and for us to look at the project and see how we can further improve in terms of the energy efficiency of our water and heating system.
Good one. Thanks, Peter. So I'm hearing some lessons learned there regarding using those smaller systems so you can get it into the building. I've got a question for you then. You said it was it is larger equipment than the typical, what would be there before, a gas burner, hot water boiler. What was there beforehand? Yeah, I saw in that photo that was positioned right next to some vents at the side of the building. What was there beforehand? What did they have to remove from there to fit that in? I thought, yeah, that top right photo. What was there beforehand? How did they? So
one of the challenges that we do is that they got a mix of a gas storage and hot water, electric hot water system. At the same time as well, that plant room was a storage for the building managers in terms of different equipment. So we have to negotiate with them in terms of like how we need more space, we need more ventilation, we need a proper pathway, air pathway from point A to point B. So we do need to negotiate with the building managers how to repurpose the plant room accordingly, so that the heat pump is fit for purpose for the heat pump to be placed there.
Gotcha. Thank you.
Yeah, so you can see how, I guess it's like the shot is just like how messy initial plant room is. They need to remove a lot of pallet racking equipment parts to make it fit for purpose.
Sounds like people had to be fairly flexible there as well to get that to happen. Thank you very much, Peter, Norman, Chun, and much appreciated. Lots of good practical experience there, and good to see this being done and things happening in practice. We are just a tad over time, so I'll get you guys, if you could open up that Q&A box and type in some answers, and then everybody should be able to see that. That'd be great. And just to wrap up here, I'm just going to bring Ahmed back in, and we're just going to review a little bit of the key lessons learned there and how that fits into the overall thinking. Ahmed, quite a few issues there which were raised and important for that designing and sizing that heat pump.
Yeah, sure. Thanks, Jared. I actually owe a big thank you to the ESW team, not only for this excellent presentation and excellent case study here, but also because they have been very supportive of us during the development of this guidance document and the body of work that we have done in this project. For example, this part of the webinar here that I'm going to explain is heavily based on the experience that these guys have gained throughout all those projects, and they have shared us with their generosity. On this slide and on a few other slides that you will see later in this webinar, we have this sort of charts that explain just only synopsis of the content that we have put into the guidance document you will see in a few weeks. I mean, on the right-hand side, and on the left-hand side, you see the same procurement guide that Jared explained at the beginning of the seminar. On the right-hand side, what you see is the key elements of the design considerations that we have covered for this. We have highlighted for this specific application in the guidance document. All the time, the central component that we have defined there is understanding how the energy flows in an application. But perhaps I should say that for this residential buildings, most of the time we are aware of the energy flow and the thermal demands. If we don't know that, we should definitely run an audit and understand it. But if it is available, then it is like a less of a concern. However, building upon that energy profile of the building, what needs to be done as the cheapest option to improve the successful implementation of a heat pump is go through the first step of energy efficiency improvement on the site. And easy options for energy efficiency improvement to be able to reduce the load includes, for example, better air tightness or a better thermal insulation of the building. But it is not only this. We do not have time to go through all of them, and we refer the audience to go to the report and to the guidance document, see a full list of these aspects there. The second important design consideration is the water temperature. Most of the time, the supplied water temperature has been selected according to, let's say, for example, hydronic heating system requiring 80 degrees C, for example, temperature. But we know that with improvement of the heat transfer rate from those heating elements in the building, we can run the entire system at a lower temperature. So that needs to be revisited, and by increasing the heat transfer of those panels, we reduce the required temperature and enable more heat pump options to deliver the heat. Of course, load smoothing with the use of thermal storage and controlling the load. For example, on the domestic hot water application part of the application, what we can do is we can, let's say, reduce the flow rate if many features turn on, like hot water taps turn on to control the load. Of course, waste heat recovery. You guys in your presentation, your slides presented the opportunity of waste heat recovery. If waste heat is available in the building, we definitely want to utilize it to help the heat pump operate at a higher COP, and also avoid icing of the heat pump in those extremely cold conditions. They are rare, but if we can eliminate them, that is very beneficial. The space constraint, you guys spoke about that brilliantly. You provided an example of that. What we mean by that is the required floor area. We have talked about that in the guidance document, and also the noise that needs to be controlled, and of course the microclimate effect that, again, you guys explained there. And we need, with microclimate effect, what we are referring to is being able to avoid temperature drop around the heat pump system just because of their own operation there. And the auxiliary heating, it was very interesting to see that ESW is utilizing the on-site PV as a extra heating to raise the temperature inside the tank. If we require a higher temperature beyond the capability of the heat pump, we can use auxiliary heating for different purposes. For example, one example is to suppress Legionella growing in the tank. And also another aspect that requires auxiliary heaters, sometimes we call them like backup heaters, is when during very cold conditions, when the thermal load is high and the COP of the heat pump is relatively lower, and the auxiliary heater can come in and compensate for that.
Okay, Ahmed, let's we need to move on, Ahmed.
Sure.
We do need to move on to make sure the other case studies have enough time. So let's move on. But you'll see when you get these slides, there's also some highlights there for the procurement issues that may have been raised and could have been handled there as well. Good one, very much. Thanks for that that case. Next one we want to talk about is dairy, and I think we have to start by apologising to the dairy farmers that will probably watch the recording here, that we had our webinar here today right in the middle of the afternoon milking. So first of all, apologies there, but do hope you get a chance to watch the video. But we want to talk about dairy farms, some 4,000 or so dairy farms across Victoria, and heating up of water is a major cost for them. There was a big push on heat pumps in the late 2000s there, and it was adopted quite widely, up to about maybe 30% of the dairy farms in Victoria. However, it was not a pleasant experience for most. They were often domestic or residential grade heat pumps, and there was a lot of failures and problems with those. And from what we understand from our research, at least 2/3 of those have been removed out of dairy farms, and it does have a bad name, that these lower quality heat pumps that went in there that really weren't fit for purpose. Some people had really nice clean water and clean conditions, and they've survived with their heat pump and they love them, but unfortunately that was not the majority. What we see coming out now is this sort of second generation heat pump, which are much more about a commercial grade, can handle higher temperatures, and really can handle the poorer water quality much better. So it's great to see this next generation of heat pumps coming forward, but still a lot of lessons to learn, and still a lot for that market to develop, where people and farmers have a very good choice of different suppliers in this space. But we certainly see us developing, and a really large potential to help that industry there. So let's dive in and have a look at a case where that has been used. A heat pump of this second generation has been employed and is operating, and have had success and great results. So I'd like to welcome Mario Como, the Senior Project Manager working at the Ellenbank Smart Farm there in Gippsland, along with Greg Morris, the Senior Technical Officer. And so Mario, if I'll get you to share your screen and take us through how you guys went on your journey with heat pumps at the dairy farm. Yep. Do that there.
Tell me if you can see it.
We got that one. Go for it. Thanks, Mario.
Okay. All right. Good afternoon, all. Greg and I are looking forward to presenting the hot water CO2 heat pump setup that we set up at Ellenbank Dairy Farm. We'll just share this presentation. I'll get Greg to do an introduction on the farm. So Greg, I'll just hand it over to you. You can explain what the farm actually does.
Yeah, thanks Mario. I just suppose putting it into perspective in regard to, commercial size dairy farm. So the Ellenbank Research Farm, we're here to provide research ready resources. So it's not only for the industry itself, but for a whole group of scientists that do their work out of the property here. We operate the farm on a commercial level, of course. It's a pasture-based system. It's about 175 hectares of perennial pasture. The remaining land is sort of covered with shedding and wildlife areas and riparian zones for creeks and so forth. We do have a 50 hectares of support area. We milk about 450 spring calving cows, so quite important for establishing your hot water supplies is your calving patterns. We produce about 3.1 million litres or 7,500 litres on average per cow per year. So production wise, definitely representative of the industry. And as mentioned, it's a pasture-based system, so probably total of the diet is about 60%, and the balance is grain and other purchased in fodders and feeds. another big part of the Allumbank Smart Farm or Research Farm has been a project that we've been looking at becoming the first carbon neutral dairy farm, and I think that's actually in the world. So I know when that was announced by our directors, it created a lot of interest internationally, and you know, it was how we were going to go about doing that. So the big things we've looked at, and energy is one part, but it is also the methane produced by the animals, and you know, that's a big part of what the research farm is focusing on. But as a part of this project, we've actually installed a number of different systems to try and improve energy efficiencies, and that's, I suppose, you know, we've got some lithium ion batteries, some zinc bromide batteries, doing different things for transferring water around the farms, for reducing the input costs, obviously. And that's where the CO2 heat pump system, you know, really came into this project well, and you know, and to give us the ability not only to try it for ourselves and to get it working, but to help farmers and be able to demonstrate that these technologies can work, and you know, and what those benefits are really in farm and how they operate. So yeah, thanks, Mario.
All right. So just the heat pump, why we're using it. So hot water is required to sterilise the piping and equipment after milking. Hot water is required to be above 80 degrees to ensure the system works correctly. So we stipulated on our contract that 80 to 85 degrees was a requirement. So just going through the old hot water system, it was a 2 by 1,250 litre electrical hot water tank system, they were each rated at 24 kilowatt electrical power. We also they were supplied by a preheated LPG gas system and a heat recovery system from the chiller. Hot water delivery was about 2,500 litres. Recovery rate is roughly twice that of a heat pump, so 800 litres per hour. And the new system we installed, which you see on the side there, it's a CO2 heat pump system. It's a 26 kilowatt heat capacity, 8 kilowatt electrical power rated. We put in 2 by 1,500 litre tanks. Refrigerant type is CO2. Heat recovery was removed from the system and diverted elsewhere, and we will explain why we did that. And we call the hot water tank 83 degrees, tank 1, and the warm water tank 2, 60 degrees. The recovery rates 400 litres per hour. So this next slide is just to describe. So what we did, we installed the system in November last year, but prior to November, March, we made sure that we did have energy monitoring that area. So we got a good representation of what energy that we were using. So with this system, we made sure that we got an online system consisting of electrical power consumption, water flow meters, and tank temperatures, for tank 1, tank 2. And that supplied us a good daily snapshot of what the system was, how the system was performing as we installed it. So just the system setup. So this is the system after hot water's used, and I'll call it system off stage. So tank 2 sits at 60 degrees and is full. Tank 1 sits at 83 degrees and is over half the capacity. And we have a solenoid valve in the closed position. So this is basically at the off time. And so when the system starts to heat, we actually open up the solenoid valve, and we'll explain why we actually do that later on. So cold water comes into tank 2 at about 20 degrees, and that tank 2 water, which was at 60 degrees, moves into tank 1, and that's at 60 to 65 degrees. I've just called it 60 degrees, and the system starts, and it gets to its final temperature stage. Now, it was claimed that we could achieve 90 degrees and we've gone through the system, and the highest we've achieved is 83 degrees, which is what we require and within our limits. So the tank reaching 60 degrees, tank 2, the CO2 pump system stops, and we have a ready stage position. So the farm, the dairy farm, has the water available, hot water available, and ready to go. So in terms of the issues and solutions, Greg, do you want to start off with the first one?
Yeah, thanks, Mario. So yeah, we're just going to go through, or more so Mario's just going to go through some of the issues or solutions that we had with getting the system up and functioning, and more to the point suit the requirements of the farm. So a couple of the key points, and one of the main ones is what we needed to do here was to establish a backup hot water system. We weren't sure how long the install was going to take. Obviously, being a dairy farm, it's we operate all year round. So we had to make sure we had the correct volume, not only volume, but temperature water to maintain that hygienist system while we continued the milking. We did this just utilising a heat recovery tank that we had basically spare, and made use of the instant gas system that originally supplied the electric hot water services. And look, it really worked well. It maintained that temperature very well. So Mario, I think we're up to you, mate.
Yep. So in terms of the system, so the initial performance of the system, the hot water temperature was well below the stipulated temperature requirement of 80 to 85 degrees for the dairy plant to maintain hygiene. So the first thing we did, we had the heat recovery from our chiller, which is about 52 degrees, going into tank 2. So we actually took that heat recovery away, and we're using that heat recovery water in our vat wash system. And that was because the heat pump was switching off. It was reaching 60 degrees on that tank 2 and switching off because of the return loop reaching 60 degrees, switching off. So we then installed a solenoid valve and a timer to divert that water, tank 2 water, into tank 1. And this water needed to be supplied twice a day for morning and evening milking periods in large volumes. We also found that having the system ready for 10 hours, the guys before described a well-insulated tank. The tanks are well-insulated, but there is a temperature loss, whether it be 2 to 5 degrees, that we noticed just looking at our data logger. So we actually made sure that we turned on the system just before we required the hot water. So about 4 hours before the milking period started. In terms of having a backup system in case the heat pumps failed, so we made sure we had an electrical element system in place. So we haven't had to use it, but we can go from auto to manual, and it'll divert to the electrical element system. We also we placed a manual bypass valve, and that was just in case the solenoid valve failed. We could open up the manual bypass valve, and we can shift the water from tank 2 to tank 1, and the heat pump will continue to operate and reach temperature. We also found that we installed an additional outlet in the hot water tank, tank 1, to provide the staff warm water, 60 degrees, because as the system is running, the tank 1 is starting at 20 degrees and reaching that 60 degrees. So they don't have, if you have a water outlet on tank 1, so tank 2 at 20 degrees, it's not doing anything for them. So that was for PM milking and AM milking at low volumes. So in terms of the key learnings, so understanding your system capacity, hot water volume and temperature requirements, that's very important. So with the farmers, you can't expect the farmers to know how much water they need or they've been using. It's mindful that the suppliers or the designers get in there and measure it for them, because you can't rely on their data. And we had good data prior, so we were okay. Understanding electrical consumptions of your existing system is critical, so you can make comparisons and check to see whether the system's performing. Get your CO2 heat supply system and installer, which is the plumber in our case, together early to discuss. So I got them both, well, actually Greg, the plumber, and the supplier got together at a local show and demonstrated the unit, and we were quite comfortable and convinced that the system will work. Look at a backup system to maintain existing system, which I've just showed you. Monitor system parameters, temperature, volume, electrical consumption. Now we've got continual data monitoring. This can be done via a BMS or an online system, but if you can't have that system, at least manually check and monitor those numbers, whether it be temperature, a water meter or electrical meter. Ensure that you have a maintenance plan in the system. So there's minimal maintenance on the system. We've done a 6-monthly maintenance check, and it's just basically just checking the overall system, making sure there's no excessive noise, things are running okay. And we've got a yearly maintenance check to do, which will be a bit more on that check. And what tends to happen with hot water systems, they seem to be reliable. They'll run, and it's not until they actually break down that people start having major issues. Ensure temperature sensors are installed in the ideal position and reading correctly. So temperature sensors being installed on top section of the tank compared to the bottom section of the tank can give you different temperature readings. Consider the footprint of the system. Maintain recommended clearances for the CO2 heat pump. So, front, rear, sides, and even the top of it, you should have clearance as per the design of the unit. And work together with supply, installer, and user, and to achieve the result, which is what we had to do. Understand your electrical consumption of the new setup as being the final. So we had no lost time, no issues, but we had a backup system in there, and we mitigated any risk in that sense. So in terms of getting the system up and running, it's been running for about 7 months now, and we're quite happy at the moment. Yeah, that's us for now. If there's any questions.
And thanks very much, Mario and Greg. Yeah, a really good summary there. And there's a question come through about the project cost and return on investment. Any sort of high level numbers you can point towards here for the project?
So we know the return on investments, it's quite high. In terms of the project costs, we had to replace the system. So the system was 2002. The original system was 20 years old. So we had to incur those costs. So, for instance, to replace the tank with electrical hot water tank would have been about $17,000 to $20,000. It's equivalent to what the tanks that we got from for the CO2 heat pump system. So in terms of costs, I can't give you exact numbers, but we're looking at a payback of 6 to 10 years, and that's taking into consideration the replacement costs being our main instigator in that sense. So in terms of energy savings, we're saving about $6,000 a year. We've completely eliminated the gas. We've got to just go back and check to see how much gas we were using for the farm. I think it's about $3,000. So it's been running for 7 months, so we're just establishing our final numbers, and we'll have those pretty soon.
And of course, on your way to decarbonising there as well. Many thanks for that, Mario and Greg. And I'll go back now and we'll just do a little quick summary. I've got Ahmed just to go through a few of those key issues once more. I think this will steal the presentation back from you. Ahmed, could you just very quickly run us through this one just in 1 or 2 minutes? In the background, Mario and Greg, there's a couple of questions come through. If you could open up that Q&A and feel free to type in a few answers there, that'd be great. But Ahmed, just 1 or 2 minutes on this one.
Sure. So the way we are capturing the important aspects of the lessons actually you guys learned to capture that in our guidance report, we are saying that the understanding of the energy flow, as you said, is a central part again. And most of the your talk, Maria and Greg, was about the water temperature, how important that is, and how it is affecting the entire design. We talk about that in the report. We highlight the maximum temperatures required, and also the thermal storage design and selection and integration of that with the heat pump to be able to maximize the utilization of the heat pump and also reducing the running cost. You mentioned something very important, that you want to minimize the duration of the hot water remaining in the tank to minimize the heat losses from there. And that's actually an important aspect. We have talked about that about the heat loss of the storage systems in our document. Waste heat recovery, again, as you mentioned, from the milk chiller to be able to partially offset the required heat from the heat pump, and the auxiliary heater, whether it is to increase the temperature of the water to suit the cleaning processes, and also as a backup during conditions that more heat may be required, and the heat pump does not need to be necessarily designed for those extreme conditions and be oversized. Similar to the previous one, if you look at our procurement guide, procurement criteria, you will see that we have emphasized on the quality of the products. And as far as I see, you guys in that project, Ellenbank, have used quality products as you explained there. So the quality of the products, the compressor, the heat exchangers, especially if it is going to be used in places that might have higher risk of corrosion on the equipment, are important. We have highlighted them there, but it doesn't mean that other aspects that are in grey there are not important. They are also important to Jared. I believe that was 1 to 2 minutes, so I saved time for the rest of the presenters today.
Oh, yeah, thanks, Ahmed. We'll make sure we got time for the next one. And just one quick comment there. We hadn't highlighted space constraint, but it did end up being an issue for this one, if considering the microclimate effect. It was always thought for a dairy farm you're going to have a reasonable amount of space there, but yeah, if you don't have enough space around that heat pump, you'll get this microclimate effect happening and cold air going back into the heat pump and efficiency issues there. So we might have to get space constraint back on there for dairy farm to remind them about that as well. Brilliant. Thanks, Ahmed. And very many thanks to Greg and Mario. And if you've got some questions, they're online, so put them in that Q&A and they'll be able to open those up and answer you there as well. So let's move on to our final presentation case study to look through today, and that is aquatic centres. And we've got Brendan joining us from Bridgeford Group. But before he does, let me just give you a little bit of context on aquatic centres. There's some 200 reasonable size aquatic centres, maybe up to 400 or so if you include swim schools within Victoria. Some 3 or so petajoules worth of gas usage down there. So this is a really big issue and big opportunity for Victoria to reduce gas and to decarbonise. Heat pumps are well used in the warmer states, certainly from New South Wales up, very commonly used, but not so commonly used in Victoria and Tasmania and all South Australia. In the past, low gas prices have encouraged the usage of CHP or combined heating and power systems, basically a big gas engine. But now with high gas prices, that is not looking like a great option. And combine that with what is seen as very high maintenance costs is not seen as a great option with those gas engines. So people are certainly looking to get away. You've got local councils who want to get away from gas and decarbonise. So you've got plenty of momentum there. What we also see affecting the market is this, I'll say, next generation of aquatic centre heat pumps where they use low charge ammonia. That's the LCA, low charge ammonia heat pumps, and we see that's perfectly matched to the demands of what an aquatic centre needs in terms of its heating requirements. From that you can get very high COP, very good industrial grade equipment, and really good efficiency overall. And so we see this being a big part of that going forward, as well as implementing better heat recovery and better building insulation as well. We know that a lot of aquatic centres have been designed to look nice and have lots of glass, but a very poor thermal performance. So lots of potential here, and so we thought we'd explore this further. And so joining us today we have Brendan Voss, and I'm not sure if Nick made it. Nick was a little bit of a question if you'd make it there, but we definitely have Brendan Voss online, the director for Bridgeford Group, who has worked very closely with these aquatic centre upgrades. And Brendan, I'll ask you to come and share your screen and take us through the projects that you've been looking at. Stop sharing of mine. Yep. Brendan, that's come through, but I can't hear you as yet. Maybe a mute going on there.
Unmute, and I'm going to put my video on, start video. Okay, the host has stopped my video, but aside from that, we're all good. So, cool. So firstly, just want to say thanks to A2EP and everyone for having the opportunity to present. It's really great to see so many people online and some really cool case studies. So thank you. I joined Bridgeford Group in October last year after spending 9 years with Smart Chiller Group. So see a few familiar faces in the audience list. So yeah, good to see that. Since I joined Bridgeford Group, I've been really fortunate to be part of multiple energy transition projects, predominantly focused in asset electrification, particularly just gas assets in commercial buildings. Let me just make sure this slide is going this way. So I'll just give you a bit about Bridgeford Group. So we work primarily in the retrofit space. We focus on practicality as part of what is a much bigger integrated energy and infrastructure picture. So since October, we've worked on now over 120 buildings, 150 buildings in facilities such as universities, office buildings, aquatic centres, many others. All these projects have ranged from roadmaps to feasibilities to detailed engineering designs, which has been really good to be part of. One of these projects is actually Cardinia Aquatic Centre, which was initially done as a concept in August 2021. It's just a feasibility study to help inform the City of Geelong on their electrification pathways. This project's now in detailed design, so it'll be good to walk you through some of that as well. As we know, retrofits are typically bound by a lot of constraints. We've heard some of those today, space, power being the two primary ones for electrification. This project had a little bit of everything, including an integration into what is a wider net zero emissions pathway for the City of Geelong. And we are lucky enough to have Stephen Rodwell on from City of Geelong today in the background if there are any questions to do with what that wider context and net zero emissions pathway looks like for them. So being that I wasn't here when we first did this concept, I'll hand over to Nick, who's our managing director, who will walk you through the project itself. So,
great, thanks, Brendan, and thanks for having us on the line here. Brendan will be controlling the screen as well, so I have to remind him to click next. So the site in question is Cardinia Aquatic, so it is right near the Cattery down there in Geelong, and worked quite well for Brendan as he is a Geelong supporter. I'm a doggies man, so I felt like going to enemy territory down there. So in terms of the project overview, what prompted this project? Firstly, Geelong have a net zero target 2025 for own operations, and one of the existing boilers was coming to end of life, and that then presents a key opportunity to electrify the site. They also, during COVID, I believe one of the councils had promised that the centre would change from seasonal use, I think from November to March to all year round, or maybe it was October to March, all year round. And that presented challenges in terms of could the existing plant or the new electrified plant cope with that increased operation. So the opportunity here is how can we maximise the emissions reductions to net zero via electrification? I suppose that's within the constraints the facility itself, which we talked a bit about with the other case studies today. Brendan, I'll get you to go to the next slide. So just a bit of an overview of the site. 6 pools there: FINA pool, Olympic pool. So they're your large pools. It is an outdoor aquatic centre. Diving, water slide, learner, and toddler. And they are serviced by a centralised plant with 2, I believe, 800 kilowatt boilers there. And the site has existing electrical constraints, which is not uncommon for aquatic centres. And I believe the transformers, I think it was 500 kVA or 315 kVA. So it does present challenges with electrification. High existing gas consumption, being an outdoor facility. So the requirement to make sure that we have not only the reduction in energy, but also providing the load that's needed. Geelong purchased their electricity from VECO, the Victorian Energy Collaboration, meaning that it is zero emissions electricity. So it does present as a great opportunity to go from natural gas to electrified hot water. From an operational perspective, the change in operation from seasonal to year-round proposed some challenges. Various water temperatures as well across the system. Some pools operating with covers, some without. Next slide there. So something that we focused on, particularly at the concept phase, was to say, well, what will it look like to fully electrify the system, and is there a partial solution that might work given the site constraints and I suppose the diminishing returns as you fully electrify. We developed a calibrated pool simulation model to determine the optimized heat pump sizing and provide the financial benefits of electrifying. This model included directional wind speed, sources of heat gain or loss, including evaporation, conduction, radiation, ability to convert from seasonal to year-round, calibrated against actual energy consumption, as well as local weather data, temperature, relative humidity. By doing this, we were able to see the alignment between the operation of the current equipment sizing and model. So our model wasn't saying we needed 3,000 kilowatts, but it was fairly close to the 1,600 was there. The year-round operation didn't mean there may have been a small change required into the capacity, but not drastic. And an alignment to the baseline energy data. Now, given the pool load was driven by evaporation, wind speed, or ambient temperature, humidity, this model produced some interesting results. And what we can see here with that heat load distribution is that 45% of the year, the load is under 400 kilowatts and under a megawatt for 80% of the year. So what we actually looked at was partial electrification to provide the best bang for buck from an emissions reduction opportunity. Next slide, Brendan. So we presented a number of options here, which is shown on this slide. So what the current system was to operate, including offsetting of those gas emissions, a boiler upgrade only, heat pump at a 400 kilowatt and 800 kilowatt, and then fully electrified. And you can see there's a drastic uplift in payback for the fully electrified solution because of the need to upgrade the transformer and incoming feed and all the electrical infrastructure, while the partial electrification option can sit within the current electrical confines of the site. Something that we do focus on here as well as marginal uplift. As one of the boilers is at end of life and will be replaced anyway as part of that sort of maintenance upgrade budget, we looked at what the cost uplift was to electrify from the business as usual case there, and then what the payback on that uplift be. As you can see here, some pretty attractive figures here because of the high hours of operation proposed for those heat pumps that aren't sitting at peak load. Next slide, Brendan. So we've got a few key takeaways here, and we're terming this sort of operation-led design. And by sizing for partial electrification, you can put in a heat pump. It doesn't fully electrify the sites, but it's sizing it for, let's say, half capacity, 800 kilowatt instead of 1,600. You actually get close to 90% of the emissions reduction, because you're having those heat pumps run so many hours in the year, and the pools themselves are a bit like thermal storage tanks. And if you think that you may have a fixed budget to spend on electrification, you can either spend it all at one aquatic centre and fully electrify, or you could spend it across 2 aquatic centres, and you have the potential to get up to 1.8 times the emission reduction combined between the 2 aquatic centres than one. And that's some of the thinking that we've employed here to say, well, at some point you want to fully electrify, but to get the best bang for buck now and the most emissions reduction today, actually do partial electrification at one and partial electrification at the other, and then come back around and fully electrify those aquatic centres later. I think that's a bit of an interesting way of thinking about this, rather than just looking at it with one facility in mind. As I mentioned, that focus on marginal uplift and savings compared to BAU asset replacement assists in payback. Otherwise, you're seeing these paybacks look quite high, but you're not capturing that either avoided capital cost or that business as usual upgrade should occur. And with that, the partial electrification is designed within the constraints of end-of-life electrical infrastructure, pool operation and load. We weren't too spatially constrained on this one, which is lucky. But some of the other aquatic centres we're working on, which are in more urban settings, have a lot of spatial constraints there. Other opportunities and considerations, as mentioned, the pools do act as thermal storage systems for the heat pumps. So you have the ability as well to float set point, particularly if there's a high requirement for peak load, but that might only occur 1% of the year. If you're okay with the temperature in the pool floating lower during those periods, you can size the heat pump smaller again. The addition of or regular use of blankets will drastically reduce that energy consumption. If you can cover it when you're not using it, it's fantastic. The other thing that was very interesting is the wind speed. And there was a graph with the load duration curve a few slides back that showed the effect of wind speed to evaporation loss. And something you don't see a lot of, but can be actually a really good energy saving measure, is looking at wind breaks around the pools to stop that high wind speed directly over the pool surface, contributing to evaporation. The benefit for Cardini was we have the stadium right there, which does help somewhat with the wind over the pool. And I think that may be pretty much everything. Brendan, do you have anything else that you would like to add to that?
No, so just obviously all of those key takeaways are applicable in all the other aquatic centres. I think that we've dealt with. Some are, one we just spoke to is looking at one outdoor pool and a combination of indoor pools, and we've looked at some indoor aquatic centres. Obviously wind velocity, a bit less of a problem in an indoor aquatic centre, but you get a bit more of a spatial constraint. So each one of these we've looked at has been integrated into a wider net zero emissions picture or a pathway for a client. We're lucky that our clients are looking at it from that perspective, and yeah, we're glad that we can help them on that journey. So that's it.
Fantastic, and really inspirational way to look at those problems and solve them, thinking outside the box there and thinking forward. Stephen, any comments, observations there? It sounds like you guys are on a great journey.
Yeah, I think it's from a council perspective, it's great that there's people willing to share their expertise and guide us along the journey. We're looking at 21 sites with varying levels of gas to electric conversion involved. So it's pretty confronting, and there's a million variables. But yeah, certainly it's a great community, I think, out there, and I see a few names in the attendees who have certainly helped us on our journey. So great to share the information and move forward with this.
Brilliant. Wish you all the luck. And that electrical transformer upgrade, we've seen that in other cases where that really does blow the case right out of the water. A couple of solar panels on the stadium next door and behind the meter, and boom. But I don't want to tell you how to. Good one. Hey, Ahmed, are you there? Let's have a quick look at how some of those key issues and how that affected, and so we'll see those in the guidelines as well. If you just we'll try it for 1 or 2 minutes once again. Hey, Ahmed.
Yeah, sure. It is very exciting to see that actually the actual experience out there is supporting the arguments that we have been making in the guidance document. For example, Nick spoke about the heat loss from the surface of the water because of evaporation from there, and the impact of wind speed. We have brought many of those items, including that one, under the heading of energy efficiency in an aquatic center. And for outdoor pool, it is probably a little bit more challenging. For indoor pools, we discussed how, for example, increasing relative humidity in an aquatic center can reduce evaporative heat loss from that surface. Then we talk about water temperature there, and in many cases throughout this work, we have emphasized that heat pumps are not one-to-one swap. You do not need to stick with the existing design. For example, for water temperature, when you are switching to heat pump, you can revisit that, reduce that temperature if it is possible. Load smoothing, very interesting to hear you guys talk about the utilization of the pool itself as a thermal storage. That's a massive amount of water in there with huge thermal loss, and it can help to smoothen the load there by, for example, slightly increasing the temperature of that body of water, and it can be actually like an intraday sort of intra and intraday sort of thermal storage. Lots of opportunities for waste heat recovery in an aquatic center. We have spoken about them in the guide. One of the important things is that there is a huge amount of latent heat in the exhaust air from aquatic centers. At least several analyses have shown that at least 50% of that heat loss due to evaporation from the surface of the water can be captured by heat pumps, because they are able to condense that moisture of that air and capture its latent heat. You spoke about a space constraint. It is, as you said, it is sometimes an issue there, sometimes it is not, but it is still there, and we need to consider that. And very interesting to hear from you guys that auxiliary heating, how you are approaching that. We have mentioned a backup heating in our document. It is similar to the idea you guys explained here by saying that we go with 80% electrification and still use, for example, other sort of heating technologies for 20% of the time. If you look at air procurement, probably the most important thing we have highlighted there is that the heat pump needs to be industrial grade sort of heat pump, being able to resistant to corrosion, high on time, low maintenance, a very reliable sort of heat pump. So I do not waste the time now by reading through those items. I stop here in terms of that. Just one more thing, Jared, I mentioned here, and then I stop. Just a very rough estimate of the benefits that one facility can gain from the DEU program. It has been put into the small table there by replacing 30,000 gigajoule of heating requirement from a gas boiler with 85% efficiency, switching that to a heat pump that has a COP of 4. Almost 1,000 weeks can be secured for that, and its net revenue at the current price of these weeks is estimated to be around $60,000.
Brilliant, many thanks, Samad. And yeah, we do see that VEEX being an excellent assistance for aquatic centres. That 30,000 gigajoules per annum is really quite a common amount, somewhere around there. Some use more, some less, of course, but yeah, that's quite an amount of revenue that can offset that investment in the heat pump. So good to see that support there. Wonderful. Many thanks there, and if you've got questions for Brendan, Nick, or Stephen, they're online now. Feel free to put that in the Q&A, and they'll be able to get to those. We've got a few coming through there already, so yeah, go for that. I thought with that, we've got 5 minutes to go. I was hoping we could do a quick poll and see what some thoughts are out there in the webinar land there of how we did today, and we've given you some examples and 3 case studies there, and hopefully there's lots of cross learnings in between each of them there, and we're hoping to get a little bit of feedback from you. First of all, asking, you know, how useful were they, and how did we do? If you just hopefully that will come through on your screen. If not, you go to slido.com and enter in that number of 8568919, and then you'll see just enter in, let us know how you do that. next question coming after this is we'll ask you to type in, say, what was missing, what else would you like to know, and that will flavour the final version of our guideline as well. And so, yeah, hey, if you're giving us a 3, that's fine, but hopefully you can tell us what we're missing, and we'll make sure we make those corrections when it comes to do the final version of the guideline. So let's do that. So yeah, a few people coming through. We'll just give that another 30 seconds, and then I'll ask you, yeah, what was missing? What did we not cover today that you would have liked to seen a bit more info on? So please, I'll ask that question in a moment, and then we'll have one more question after that, and then we'll close out the webinar. Beautiful. Many thanks for your feedback here. I'll leave that. Looks like that's the feedback slowed down a little bit, and let's see. So yeah, please tell us what was missing. If I go to the next one, that should come up on your Slido or on your screen there. Tell us what was missing. What did we not give you there today? And look, and we may well have it in the guideline already, and that'll tick off to say, great, we've covered that in more detail in the guideline. But tell us what you think was missing there to help you inform your decision on heat pumps and their suitability, and how you install it, how you optimize it, best ways to do procurement. What do you think needs to come through there? Looking for more details there. Great. We'll hopefully, I mean, when we've got the written guide, Ahmed, I think there'll be more details than what we showed today. So yeah, and of course you'll be able to link up with a lot of suppliers here and these guys too, if you want to get more details, if you're in that same industry. We'll make sure that you've got the contacts there for Bridgeford and what have you. Indoor pool details. Yeah, it would have been nice to have that indoor pool, but this was a great case. This one in Geelong, a great case that's happening right now. There are lots of other aquatic centre webinars that we've held in the past. If you go to YouTube and look at A2EP, we've done aquatic centres going through that. The one there at Brimbank Council, St Albans. We're hoping to do an aquatic centre, one with association with DELWP and SV coming up next month. Actually, we're going to dive in and have a look at what's been happening for Yarra City Council Aquatic Centre and a few more as well. So you'll see more coming on this aquatic centre and more details there. Okay. Yeah, something about on delivering of the heat pump versus COP. I think largely we've seen that reports are that they are delivering, and that's one thing we want to do in that procurement guide, is to give you that mechanism to make sure that people do deliver as they expect as well. Okay, I've just thought we'll hit you with one more question, if that's okay. Very, very much thank you for your feedback and answers there. We'll take that into consideration and make sure that's part of the guideline, and look at how we can address that in the guidelines. Final one here is if there's any barriers that you're seeing for adopting this, the VEU activities for C&I heat pumps, feel free to type away there, and we'll give that a minute or two. I am aware that in some cases that the type of thermal storage that is possible underneath the current activity is not applicable for all types of thermal storage. And that is the case for ESW and TES that was presented today. And so there'll be no doubt hoping that some changes in maybe the next version allows for different types of thermal storage. But acronym overload, perfect. That's what we no, sorry about that. Apologies. We'll make sure there's a glossary of terms in the guide. In fact, there's definitely is a glossary of terms in the guide to help you through that. Anyone coming into this space in this industry is going to be overwhelmed, that's for sure. Grouping not flexible.
Jared, it's Jack Brown here from DELWP. So just with this question, it's really useful that people are providing their feedback. I do encourage people to email. You can email me, jack.brown@delwp.gov.vic.gov.au, or you can email the program. But we're keen to hear directly from stakeholders as well on their concerns about activities. I mean, this one, but any others they might have as well.
Excellent. Many thanks, Jack. Good. So there's a few comments there, and look, DELWP didn't prepare this method on their own. There was lots of consultation already, but and you certainly see working with government, they've got constraints they've got to go through, and things do take time. And I know they've done the best to have a system out there that's going to work for all and be auditable and measurable and have the right probity ticks. So yeah, I'm sure there's ways to get these heat pumps measured and onto the system. So I'm sure that will happen over time now. Very good. We did see on that last webinar we did that when we asked who's looking at registering an activity, and there's a large majority said they're looking to register an activity in the next 3 months. So that was good to see. Okay, let's just, if I just close this out in the final minute then. Look, we've run you through today the different steps there, but we do see there's a big need going forward to help with that feedback. We know there needs to be a lot more of this. We can't wait 2 or 3 years and can't wait till Bridgeford has completely done their job in Geelong and find out the lessons learned 3 years later and implement that in the next round. So we are hoping to see a lot more of these forums come in, so we have live feedback during projects, things like what's happening at Bringbank Council and Yarra City Council and their projects, and make sure that's happening. So we are looking for ways to make that happen. There is lots of resources out there and lots of heat pumps there. You can go to A2EP's website and you'll see there's plenty of different webinars and what have you if you want some more info there. We also have lots of case studies as well. If you go to futureheat.info, plenty of case studies there on heat pumps, and it's a great resource with tools on sizing of heat pumps and things there. Finally, there is here's a list of resources, and this will come up there in the slides, and you'll be able to click on those. And so, yeah, plenty of momentum happening with heat pumps, plenty to look at out there. And just looking ahead, just to let you all know, A2EP is doing a conference, a 2-day conference in Sydney, Innovation Exchange, where we're going to bring together a lot of innovation happening for decarbonisation and hear from some really good speakers there. So there's a date for you to put aside. You'll see more information on our website and more information coming out shortly on that as well. And with that, I think we've maybe just gone 1 minute over. So many thanks for those for staying with us. And we do appreciate the presentations today. So many thanks from Norm, Chun and Peter, as well as to the dairy farm there from Mario. And we also had Greg speaking there as well. And then finally for the aquatic centres, Brendan, Nick and Stephen. Many thanks for joining us today, and Jack, many thanks for supporting this initiative, and it'll see some fantastic installations of heat pumps and decarbonisation. And so with that, from Ahmed and myself, thanks for joining us, and wish you all a very pleasant afternoon.